Okay everyone, in today's video we're going to talk about vertex problem word problems. And these word problems are going to come in the form of a maximum or a minimum. When you're reading a word problem and you're trying to decide which strategy to use, first you need to look for the terminology being used. And anytime you see the words like maximum, minimum, highest, lowest, most, or least, you know that you are looking for the vertex. Sometimes you won't be given an equation, so obviously you need to create an equation, and we are going to use that completing the square technique in order to find the vertex. Obviously, when useful, you should be drawing a diagram as well. Let's look at our first example here. A rectangular playground with one side being attached to the school is to be fenced with 400 meters of fencing. What are the dimensions of a playground with maximum area, and what is the area? Let's start by drawing a diagram just so we can appreciate what the setup is looking like. So we have a school over here, and we are looking to add a rectangular playground. So this area, that's my school. And we're adding a rectangular playground, and one side is going to be attached to the school, so we don't need to use any fencing for it. So I'm going to have a rectangular playground. Let's just make it look like this. And I only need to fence in 3 sides because it is attached to my school. I don't need a third side there. I have 400 meters in total of fencing that I can use. Now we haven't been given an equation to work with here, so we need to start by creating one. Okay? We're going to start by defining some variables. I'm going to let length, or L, represent the length of the playground. So this is going to be L. I'm going to let W represent the width. And finally, I'm going to let A represent the area. We know that we have 400 meters in total of fencing. So I know that 400 has to be equal to length plus width, or 2 lengths plus the width. I also know that I'm looking to find the maximum area, so I need an area formula here. Area is length times width. Just like we have done in previous problems, we need to isolate one of our variables in the left-hand equation in order to substitute it into the right equation, and that way we can solve for that variable. I'm going to isolate for W because it is already on its own, and I'm going to say that 400 minus 2L is equal to W. So now I can substitute that information into my area equation. Let's go ahead and expand so that we can get ourselves to standard form. L times 400 is 400L. L times negative 2L is negative 2L squared. And I'm just going to rearrange to pull my L squared to the front. Okay. Now previously, you would have been able to factor. In order to find your dimensions for L, you would have to find the halfway point in order to find the vertex. Highly complicated. So from here, what we're going to do is we are going to complete the square. Okay? I already have my first 2 terms isolated, so I don't have to worry about isolating them. I do need to factor out my A value here of negative 2. So I'm going to factor out negative 2, leaving me with L squared minus 200L. Now I need to figure out what my C value is. So my C value is going to be negative 200 divided by 2, and then all squared. So I'm going to do negative 200 divided by 2, gives me negative 100. That squared is 10,000. So I'm going to do Negative 2 times L squared minus 200L. I need to do plus 10,000 and minus 10,000. So plus 10,000, one more, minus 10,000. Okay. I'm going to isolate my perfect square trinomial, and I'm going to factor all in the same step. So I have negative 2, and it's going to be L minus 100 all squared. And then I still have this negative 10,000 hanging around. Okay. Now I need to, in order to get rid of these square brackets, I need to distribute my negative 2 in. A is negative 2, so we'll do negative 2 times L minus 100 squared. And then negative 2 times negative 10,000 is positive 20,000. Okay, so we have our vertex dimensions here. Our vertex is going to be at 100, comma, 20,000. Let's just state that. $120,000. And what are the variables that are included in our vertex here? Well, we know that typically our variables are x and y, with x being the L and y being the A. Well, x here is 100 and 20,000 is A. So I now know that in order to maximize the area, the length needs to be 100. So this distance needs to be 100. I then have also discovered that my maximum area is going to be 20,000, and we're just going to double check that in a second. So if my length needs to be 100, what is my width? Okay, well, my width, we recall we had this nice isolated equation to get the width. My width was 400 minus 2 times L, so we'll do 2 times 100. So that's 400 minus 200, or just 200. Okay? So I can start off my therefore statement immediately, and I can say therefore the dimensions are 100 by 200, and we're dealing with meters here, so we'll add those units. And my maximum area is going to be 20,000. And if you aren't convinced that we can pull that straight from the vertex form, that's fine. Let's just do length times width. 100 times 200 is 20,000. Okay? If you're uncomfortable with that, you can show that calculation separately, but I'm not going to. So I'm going to say the dimensions are 100 by 200, and the area is 20,000 meters squared. So just to recap, we started off by drawing a diagram. We wrote out our let statements for the variables that were at play here, length, width, and area. We then used, we created 2 equations, one that involved the perimeter because we have that information, and one that involved the area because the question was asking about area. I substituted in the information for width into my equation. I got myself to standard form. I then completed the square in order to find the vertex. The vertex gave me the length dimension for the maximized area. I then was able to find the width given the length, and I could conclude with my area as well. So all pretty straightforward, and it will just take a little bit of getting used to dealing with these types of problems. Let's deal with another one here. The path of a volleyball serve can be modeled by h is equal to negative 0.04 d squared plus 0.8 d plus 1.5, where h is the vertical height and d is the distance from the server in meters. Determine the max height of the ball and at what distance from the player it was when it hit that height. Okay, so again, we are looking for the vertex here because my question specifically said max height. That's what we were going for. Okay, and so we have been given an equation here. We can start by moving it immediately into vertex form by completing the square. Let's do that. I'm just going to rewrite my equation down here. H is equal to negative 0.04d squared plus 0.8d plus 1.5. First things first, I'm just going to immediately isolate my first two terms using square brackets. Now I need to factor out a. So a is negative 0.04, leaving me with d squared. And then you can use your calculator for this one because we are working with decimals. 0.8 divided by negative 0.04 is negative 20. So this will be minus 20d plus 1.5. Now we need to complete the squares, so we need to figure out what our additional values that we need to add and subtract here are. Our additional values are going to be negative 20 divided by 2, which is negative 10, and then negative 10 squared, which is 100. So I need to add 100 and subtract 100. I'm going to isolate my first three terms here by adding some brackets, and in my next step I can go ahead and I can factor. That'll be d minus 10 all squared. This is still within square brackets because I still have my negative 100 I don't want to forget about. Now let's get rid of those square brackets. We're going to distribute the negative 0.04 in. Negative 0.04 times negative 100 is 4. So we have a plus 4 and I have a plus 1.5. And I can finish this off by simplifying and adding those two terms together. H is negative 0.04 times d minus 10 squared plus 5.5. Okay, so what is my vertex here? My vertex is located at 10, 1.5, or 5.5. Okay, the 10 matches up with my d variable, that's x, and my 5.5 matches up with my h variable. We recall from the question that we were being asked what is the maximum height and what is the distance from the player when it hits that height. So I can finish off with a therefore statement here, and I can say therefore the maximum height of the ball was 5.5 meters, and it happened 10 meters from the server. Okay, in this one I didn't feel the need to be sketching a parabola. We could have, but it would have been a little bit complicated to do. You could use technology to get a visual if you wanted a visual, but I knew that I just needed to jump straight into completing the square, and so I didn't bother drawing a sketch here. Let's look at our third and last example, which is a revenue problem. The revenue R from concert ticket sales is calculated as the number of tickets sold by the price per ticket. I'm just going to highlight that because that is a super important sentence when dealing with revenue problems. The revenue R from concert ticket sales is calculated by the number of tickets sold times the price per ticket. As in, I sold 10 tickets at $10 each, 10 times 10, 100, you smush them together. Okay. The current price is $20, and typically 100 tickets are sold. For each $1 increase in price, 10 fewer tickets will be sold. Personally, I would still go if it was only a $1 increase, but that's just me. What ticket price will maximize your revenue? Okay, so we need to figure out the maximum revenue that we are going to get out of our buyers. Okay, it's really nice that we can offer them 20 bucks, but can we up that price and really make some money here? That is the question. We're going to start immediately by defining our variables. Some of them have already been defined for us, but I'm going to start just here with some let statements. So we're just going to remind ourselves that let R represent revenue. I need to figure out as well how many times the ticket price should be increased. I'm not asked to figure out, or I do need to figure out what the new price of tickets is going to be, but the question is, what I need to determine first is how many times should I be increasing that revenue. Okay, let me just say that again. I need to figure out how many times to increase the tickets by $1, so then I can figure out what the new ticket price is going to be. I can't just jump straight to what the new ticket price is. Your second variable here is not the ticket price. Your second variable is the number of times it increases. Okay, and I guarantee you, some of you are going to assume that it's the ticket price. It's not. It's the number of increases. So I'm going to let N represent the number of $1 increases. Do not make that mistake, please. Let's go ahead and let's write our equation, okay? So we said that R is the number of tickets sold by the price. Well, the number of tickets sold, we started at 100. And we are going down 10 for every single increase, every single $1 increase. So this is going to be times 10 or minus 10 times N. So if I increase the price twice, I lose 20. If I increase the price 3 times, I lose 30. It's the number that you were starting with minus how many times or how many people go down per triple increase. Now we need to figure out the price. The price started at $20. So I'm starting at $20 and it is going up 1 times every increase. Okay? Because it's a $1 increase. I'm starting from $20 and I'm increasing by $1 for every price increase, for every step up. 100 tickets minus 10 tickets for every increase, $20 and plus $1 for every increase as well. Okay? We are asked what ticket price will maximize the revenue, so we need to figure out how to get our vertex, and which means that we need to complete the square. In order to complete the square, we need to start from standard form. So the first thing I'm actually going to do is expand this into standard form. Let's just rewrite my equation right here. R is 100 minus 10 times N and 20 plus 1N. We're going to use a FOIL to expand here. 100 times 20 is 2,000. 100 times N is 100N. Negative 10N times 20 is negative 200N. And negative 10N times 1N is negative 10N squared. Let's rearrange and combine some like terms here. I'm going to pull my negative 10N squared up to the front. I'm going to combine my 10N and my negative 200N, which is negative 100N. And then I have 2,000 left over at the end here. Okay. Now that I have standard form, I can go ahead and complete the square. So I'm going to start by putting my first two terms in square brackets. Now I need to factor out my A value, which is negative 10. So I factor out negative 10, leaving me with N squared and positive 10N. I have my 2,000 floating along there. I now need to make this into a perfect square trinomial. How do I do that? I take my 10 divided by 2. 10 divided by 2 is 5. And then I need to figure out what 5 squared is. 5 squared is 25, so I need to add 25 and subtract 25. And don't forget about that 2,000 that's along for the ride. Okay, I'm going to isolate my first 3 terms here so that I can factor, leaving me with n plus 5 squared. I got the 5 by dividing 10 by 2, and I still have this negative 25 I cannot forget about. I need to remove my square brackets now by using distributive property with the negative 10. So I have negative 10 n plus 5 squared, and then I need to do negative 10 times negative 25, which is positive 250, and then I have my 2,000 that's still along for the ride. I can now finish off by combining these last 2 terms here. And so my vertex form of my parabola is negative 10 times n plus 5 squared plus 2,250. Okay. Now recall what n represents. N represents the number of $1 increases that we are going to take. Okay? N does not represent your ticket price. It's the number of $1 increases. So we need to figure out what our actual ticket price is. Let's start by stating our vertex. Our vertex is located at negative 5, comma 2,250. That's interesting. So a vertex of negative 5, remember negative 5 represents n. N being the number of ticket price or number of $1 increases. What this is saying is that we should actually be decreasing our ticket prices by negative $5. So maybe going down by $5. So our new ticket price, okay, our ticket price, we had said that the formula for ticket price was going to be $20 plus 1 times n. Okay, that was exactly what we had written when we started off deducting this formula. Revenue is the number sold times the price. Price was 20 plus 1n. So let's go back to that ticket price. Ticket price is 20 plus 1n. Okay. N is negative 5. So we're going to insert negative 5. That concludes that we actually need to be decreasing the price of our tickets. We are losing customers. They are too much. Our ticket price needs to be $15. So I can write a therefore statement here. Therefore, the ticket price that would maximize revenue is $15. Now let's just take this problem one step further. I know that it wasn't asked, but let's figure out what the maximum revenue would be. Okay? What would the maximum revenue be? Recall that revenue was the number of tickets sold times the price per ticket. Let's figure out how many tickets were sold. How many tickets were sold? Well, the number of tickets sold was 100 minus 10 times n. Recall that n is negative 5. So I substitute my negative 5 in there, giving me 100 plus 50, or 150. So 150 tickets were sold. And now let's figure out what the maximum revenue was. The maximum revenue can be found when we multiply the number of tickets sold by the price per ticket. Okay, so revenue is going to be 15 times 150. 15 times 150 takes me to $2,250, which is the same as the y value of our vertex, because we remember the y value matches up with the variable on the outside here. So our total, our maximum revenue is $2,250. Okay? So in this situation, we were presented with just some information about the revenue. We had to create our own formula. We then needed to complete the square in order to find the number of ticket price increases. We then determined the actual ticket price, because the ticket price is not negative $5. The ticket price, we had to start from 20 in order to get there. We then could figure out how many tickets were sold at this new price and what the maximum revenue would be. Okay? Revenue problems are among the more challenging, but once you get the hang of them, they really are not that bad. Good work, everybody.